Okay, let's jump into this. Have you ever looked at a bottle of cooking oil and just wondered, is this still okay to use?
Oh, definitely. Or even how companies decide, the best buy date on food packaging.
Yeah, how long will it really last on the shelf?
It's easy to just think food goes bad, but
Yeah.
there's actual science behind understanding that whole process, how the quality changes over time. It's not just random.
Exactly. And this is where it gets, well, really fascinating for our deep dive today. We're looking at source material that connects something pretty academic.
Like calculus.
Yeah, exactly, calculus.
Hmm.
It connects that to something really tangible, like food quality.
Mm.
And that leads right into food security.
Right. We've been digging into how these fundamental math ideas, specifically differentiation and integration, are actually used in food science, of all places.
So our mission for you today is to explore one really powerful example. We want to show how integration helps us understand something absolutely crucial for food quality.
Especially in fats and oils.
Right, fats and oils.
Yeah.
It's about the cumulative effect of oxidation.
Okay, so oxidation. It's basically a chemical reaction that happens in oils over time. Exposure to air, light, heat that speeds it up.
And that's what makes oils go rancid, lose their good stuff.
That's a big part of it, yeah. It's a major reason oils degrade.
So listen up, if you're maybe wrestling with calculus right now, perhaps integration feels a bit abstract.
Get ready, you're about to see it solving a real-world problem, like right there in your kitchen pantry.
Okay, so maybe break it down. Differentiation first.
Okay. Think of differentiation as finding the instantaneous rate of change. So for oxidation, it tells us how fast it's happening right now, under specific conditions like temperature. It's like a snapshot.
A snapshot. Like checking your car's speedometer tells you your speed at that exact moment.
Precisely.
But to know if that oil is nearing the end of its useful life, you need more than just today's speed of decay, don't you?
Exactly right. You need the total amount of damage, the oxidative damage that oil has built up since it was first made.
So not just the rate today.
No, it's the sum of all that degradation, minute by minute, day by day, across its whole shelf life.
Ah, okay. So if differentiation is the speedometer reading,
Hmm.
is integration then like calculating the total distance you've driven?
That's a perfect analogy. Yes. Integration is the mathematical tool we use to add up all those tiny moment-by-moment rates of change over a period.
And when it was fresh until now?
Exactly. Food scientists can measure that rate of oxidation. It changes with temperature and time. They get a rate function. Let's call it RT.
Okay.
Then integration lets them calculate the total degradation from time zero up to the current time, T summing up RT over that time.
So they're not just saying oxidation's happening. They can actually put a number on the total oxidative load that oil has experienced.
Precisely. And that total cumulative measure, that's a much better indicator of the oil's real quality and how much shelf life is realistically left.
Better than just checking the rate at one point in time.
Much better.
Oh.
Because it reflects the product's entire history, all the exposure, all the degradation combined.
And our sources mentioned specific studies doing this.
Yeah, researchers tracked oxidation rates in things like sunflower oil, for example, under different storage temperatures over several months.
And by integrating those rates?
They could accurately model the cumulative damage. They could predict when the oil quality would significantly drop, even if it still looked okay visually.
Okay, let's connect this back to the bigger picture then. Food security. How does better shelf life prediction help there?
Well, it's huge. Understanding this cumulative decay lets manufacturers set more accurate use by dates.
Makes sense.
It also guides advice on storage. Keep it cool to slow the rate, which reduces the total accumulation over time. And it helps predict losses along the supply chain.
Which means less food gets wasted.
Absolutely. Less waste in stores, less waste in our homes, more food stays safe and usable for longer.
All because we have this clearer, math-based understanding of its actual condition.
It takes something that might seem purely theoretical from math class and turns it into a really practical tool for preservation, for managing resources better.
Right. So wrapping up our deep dive here, we've seen how integration, this mathematical way to sum things up, is really key for measuring processes like oil oxidation over time.
And understanding that helps predict shelf life, cut down on food waste, which ultimately supports food security.
Yeah, this isn't just some abstract exercise. It connects directly to the food you buy and eat and that global challenge of making sure everyone has enough safe food.
It's a practical application of calculus right there.
So here's something to think about as you go about your day. Maybe when you open the fridge later. What other things in your life are accumulating over time?
Good question.
Maybe how your phone battery charge slowly drops, or, on a bigger scale, how pollutants might build up in the environment. Could these also be better understood, maybe even managed, using this idea of summing up small changes? What else is silently accumulating all around you?